Hello and welcome to another video in this series as we learn Lean in order to write simple maths proofs. We are well on our journey now. I think this is probably the 15th tutorial. In the recent tutorials we were looking at applying pre-existing lemmas and theorems, and that's an important thing to do because whenever we write proofs we often rely on existing commonly agreed knowledge which has been encapsulated in the form of theorems and lemmas. If we didn't do that, then every proof would be extremely long and laborious because we would have to justify everything all the way back to the axioms, but we don't do that. So it's an important and very common thing to be able to do. So in the last few videos we introduced the idea of using lemmas, very simple examples. Today we're going to look at a kind of lemma which works in two directions, so that's just something a little bit new. So let's dive in. So some lemmas are of the form A implies B, something implies something else, but other lemmas work in both directions. They're bidirectional. A implies B, but also B implies A, and in order to use them we just need to be conscious of which direction is relevant for our proof and then choose it. So a simple task that we're going to look at, and as always our tasks are mathematically relatively simple because we don't want to get distracted by overly complicated algebra or difficult maths. We want to focus on the lean ideas. So most of these things you'll be able to do in your head without even pen and paper. So here we've got a product of two things which equals 0. It's a zero product. P minus 1 and Q minus 2 is 0. And we need to show that either P is 1 or Q is 2, or in this case both can be true as well. But it's the disjunction. At least one of these two things must be true. Now, as I said, we can look at this and just by looking at it we can say, yep, that's obviously true. But we want to be able to write lean proofs, which means forcing ourselves to think in detailed steps, and that's kind of what we'll practice. And for completeness I should say that P and Q are rational numbers. It's important to say what kinds of quantities we're working with, because sometimes the argument isn't valid if we're using other kinds of quantities. So when we looked at this we thought, well, this is kind of obvious, but why is it obvious? What's really allowing it to be obvious? Well, we all know in the back of our heads, it's common knowledge that the product of two numbers is 0 if and only if one or the other is 0. Let's draw a picture. So if I've got something times another thing, and if that's 0, we kind of intuitively know that this is 0 or this is 0 or both are 0, and we don't think deeply about it, but there is a reason, and that idea, which I say is kind of commonly understood, is that the product of two numbers, let's say P and Q, is 0 if and only if P is 0 or Q is 0, which also includes the possibility of both being 0. This is the idea that we all kind of carry in our heads. Now this could probably be proved separately, but we're not going to do that. We're going to rely on this as commonly agreed knowledge to make our proof easier. As I say, it feels laborious, feels over-engineered, but this is about learning how to use MathLib lemmas in our own proofs. So we'll think of this common knowledge as a lemma. For our exercise we'll think of it as a lemma. In fact, it is a lemma in MathLib. So A multiplied by B is 0 means A is 0 or B is 0. The two-directional arrow means it works in the other direction as well. A is 0 or B is 0 means the product is 0. Again, we intuitively know that to be true. So we're going to use this lemma in our example. So these slides are online if you want to kind of make use of them. There's also a blog which has more carefully written words than what I'm using to talk to you right now. If you find that easier to read and study, all the content is online for free. So this is just to remind us what we've said, that P and Q, P if and only if Q, that's a logical statement, is equivalent to both of the following. P implies Q and Q implies P in both directions. So that equivalent is important. And P and Q are statements which can be true or false. So we say that P is true if and only if Q is true. That's the words we often use. If and only if. If you're already familiar with mathematics and logic, this is not new to you. But if, like me, you were new to the world of maths and logic, then what I realized is that some phrases have specific meanings in mathematics, and if and only if is one of those special phrases. So whenever you see that, it means this. And sometimes you'll see it abbreviated as IFF. So looking back at our lemma, A times B is 0, if and only if A is 0 or B is 0, we said that's equivalent to two separate statements, one in each direction. Let's clarify what they are. A times B is 0 is equivalent to, implies A0, B0, and in the other direction, A0, B0 implies a product is 0. That sounds obvious to us, but that's just to practice taking that bidirectional lemma and looking at it in terms of the two equivalent statements. So how is this going to be useful for us? So let's draw a picture. So we've said P minus 1, Q minus 2 equals 0. So let's look at this through the lens of our lemma. A dot B equals 0 if and only if, or equivalent to, A equals 0 or B equals 0. And we know that that's equivalent to saying A dot B equals 0 implies A equals 0 or B equals 0, and the other way around as well. So A equals 0 or B equals 0 implies the product is 0. So that's, these two things are equivalent. Now, which is useful for us? Which is going to help us with our task? Well, what is it that we wanted to prove? Well, we wanted to prove that Q equals 1, so P equals 1 or Q equals 2. So we wanted to prove something about these quantities. And it looks like this first form is going to help us, because its conclusion is a disjunction and something about the multiplied quantities. So if I delete some of this, so if I apply this, I can see that A is P minus 1, so let's write it in that form. P minus 1 dot, so we're applying the lemma in this direction, and then Q minus 2 equals 0 implies this thing being 0 or this thing being 0. So P minus 1 equals 0 or Q minus 2 equals 0. So there we've got a disjunction, and with the disjunctions we know that we can prove them by cases by looking at each one. And the first case is P minus 1 is 0, and the second case is Q minus 2 equals 0. And we know from our previous work that we can look at each case in turn. Well, we must look at each case in turn and see what the conclusion is. And from here we can see P equals 1, and here we can see Q equals 2 by adding 1 to both sides. So adding 1 to both sides and add 2 to both sides. So that's what we conclude. P is 1 or Q is 2, and that's actually what we try to prove. So I know that was a little bit laborious and a little bit over detailed, but we do need to be able to think at that level of detail in order to write Lean proofs. So let's go back and remind ourselves what we've just done. So we looked at our lemma and we tried to decide which direction was relevant for us, and we saw that the forward direction was most likely to be helpful given what we're trying to prove. And so the first part, the antecedent as it's called, of the left hand side of an implication, this is called the consequent, the antecedent and the consequent, the before and after. So the conditions or the result, as it were. So this matches what we're given, and this matches what we're trying to prove. So this direction rather than the other direction is going to be helpful. And then we kind of match it up and then say, well, P minus 1 multiplied by Q minus 2 is 0. It's that form there, and therefore this form is true, which is this. That's our intermediate result, and from that, again, by looking at it, we can see P is 1 or Q is 2, but we will actually have to do the work when we write our Lean proof. So this is just writing it out. It's good habit to write out the detail because it just bridges some of the journey to that Lean proof. So we start off with our hypothesis, which is P minus 1, Q minus 2 is 0. Here's our existing lemma, which is that A multiplied by B is 0 if and only if one of those two quantities is 0. So by applying the forward direction to this, this matches the left-hand side of that lemma, which means the right-hand side is true, this one here. So this is our intermediate result. And this is a disjunction, so it's a proof by cases. The two cases are this is true, and the other case is this is true. So P minus 1 is 0 gives us P1, Q minus 2 is 0 gives us Q is 2. So these are the two conclusions, and that's our overall conclusion, which is actually what we needed to prove. Great. So the key step was applying this lemma. That's what unlocked it. Now, right at the beginning, we kind of did that subconsciously. We didn't even need to think about it. But as we write down and work towards a Lean proof, this is the key. Without this, we can't unlock our hypothesis and move towards the conclusion. So applying that lemma is going to be the key. Great. So let's write code. You can study it here if you want, and there's explanations in the slides and on the blog, but let me try and live code it and talk through how it might work. So I'm using the online Lean environment, which means you don't need to install anything. It all works through the web, but you can also use the locally installed Lean as well, and doing it through Visual Studio Code with the Lean extension is also quite nice. So as usual, we import our mathlib tactic. We create our proof header. We start with example, and our variables are P and Q, which are rational numbers. And we have one hypothesis, which is that P minus 1 times Q minus 2 is 0. That's our hypothesis. And our proof objective is that P equals 1 or Q equals 2. So what are we going to do? Well, we know that applying that lemma is critical. And the lemma was something of the form A times B equals 0 implies, and is implied by, so if and only if, A equals 0 or B equals 0. That's going to unlock this multiplication into a disjunction. So let's see if we can find such a lemma. Now, as we've said before, finding relevant lemmas is not ideal. Unfortunately, you either kind of have to know they exist, or you kind of have to get accustomed to the naming convention, and then you'll kind of use the search engines to find it. So Google is the official search engine, and my guess was that the lemma might be the name multiplied equals 0. Let's find that, and it says, yep, there's mul equals 0 is a lemma. Let's see if it's relevant to us. Well, it gives us the information here anyway. It's saying that a times b is 0 if and only if a 0 b 0. So that actually is what we're looking for. Let's click into it. Yeah, there it is. If that has no zeros, then the product of two elements equals 0 if and only if, see that abbreviation, IFF, one of them equals 0, and that's exactly what we want. And it's in two directions, so we'll have to pick a direction, and we'll see how to do that. Just out of interest, let's look at the source code for that. Does it reveal anything interesting for us? Not at this stage. It's always sometimes fun to look at the source code. Right, so that lemma was called mul equal 0. Now, how do we apply this? Where do we want to apply it? We want to, well, actually the first mistake we've done is we've not chosen a direction. So the way we choose a direction is forward is called MP and backwards is called MPR. Why is that? Let's draw a picture. So if I've got a lemma, P if and only if Q works in both directions, the forward direction of that, if that lemma was called, I don't know, A, B, C. So the forward direction is called abc.mp, and that means P, Q. And if the lemma name, say, abc.mpr is a reverse direction, so Q implies P. So that's the lemma name, that's bidirectional, and adding .mp gives the forward direction, and adding .mpr reverse direction. So R means reverse. What does MP mean? A good question. So I think it's Latin for modus ponens. Ponens. That's an N. And in the field of logic and mathematics and mathematical logic, it's a phrase that means the derivation of a conclusion using an implication. So it's kind of what we're doing here. We're concluding something using an implication. So it's just a fancy little bit of Latin. So that's kind of made its way into MathLib. We could have had forward and backwards, potentially, but they had MP and MPR. So that's kind of where the name comes from. So we need to choose forward, because if we look at the lemma, we're going in the forward direction, that way, not backwards. We want to start with the product and end up with a disjunction. So how do we apply it? So we apply it to the hypothesis. Great, that worked. So what has that done? It's changed the hypothesis to that disjunction. So the hypothesis was a product, a zero product, and now we can see the info view that the hypothesis is now a disjunction. P minus 1 is 0 or Q minus 2 is 0. Now you might say, why does it replace it? Because when we did our maths proof earlier, if you have a look, we had an intermediate result. So we had our original hypothesis, which was the product, and the intermediate result was the disjunction. Both are true. Well, I guess there's no really good reason, but it's valid because they are equivalent. This indicates equivalence. So if that's true, that's equivalent. So logically, it's fine. So that's the hypothesis we have now, and that's easier to work with now. So if we want to, so we proceed just as we do before with disjunctions or proof by cases. So there's two cases, p minus 1 is 0 or q minus 2 is 0. So let's split that, obtain HA, two separate hypotheses from H. So we can see what they are. HA, which is the first case, p minus 1 is 0, and then the later we'll have that second case, q minus 2 is 0. And it's a good habit to use focusing dots. So this is the first one, and we want to prove that the conclusion is true in this case. In this case, p minus 1 is 0, and the conclusion is a disjunction. So we choose which part of that disjunction we want to prove. We have a choice, and the left-hand side seems relevant. So we choose left. So we want to prove the left-hand side of that disjunction, this one. So we choose left. So you can see the goal has changed to p equals 1. So how do we get from this case to the conclusion? Well, we kind of add 1 to both sides. Now we could use a calc section. Let's try it. We start with p minus 1, or p equals p minus 1 plus 1. And why is that true? That's just algebra. And then we can use a substitution using that hypothesis, that first case. So that's p, I'll put brackets around it so it's clear what we're doing. And that we know is 0 plus 1. And that's by substitution and rewriting using HA. And that equals 1. And that's proven the first case. Now we do the second. And then the second case was, didn't justify that, by norm num, which is arithmetic. Great. Now the second case is q minus 2 is 0. So what do we want to prove? We want to prove the right-hand side of the disjunction. So we say right, so we pick that. You can see we want to prove q equals 2 now. And how do we get there? We can use a calc section. We can say q equals, similar pattern to before, q minus 2 plus 2 by ring, which is just algebra. And then we do that substitution from the case, which is q minus 2 is 0, which is 0 plus 2. I'll just tidy that up a bit by rewriting using HB. And then we simplify to 2 by norm num, which is the arithmetic. Right, so that's completed the proof. We can see from the Infoview there's no complaints, which is great. But actually, we can simplify this a little bit more. By the way, if that was a little fast for you and you were kind of thinking what's going on, go back to the earlier tutorial on proof by cases, because that's what we're doing. We're just, we're not talking slowly about proof by cases because we've already covered that. So worth going back and having a look if you're not familiar. Right, so how do we simplify this? Well, what we've done here is we've got lots of code here, and all we've done is add 1 to both sides. So actually we can apply lin arith tactic, which just does that. And the same here, lin arith. The tactic can do linear arithmetic, so it can take a look at this and the hypotheses and say, well, if I add 1 to both sides, I can end up with a conclusion. So you can do all that hard work. So when we started this course, we weren't overly keen on clever bits of short code that were difficult to read. We used calc sections a lot, so it's really clear what we're doing. But now as you get more comfortable, we can start, we've already done that in the last few videos, we can start to introduce some of these shortcuts if it's clear what's happening. So it should be clear now. So if we put our cursor here, we can see that the hypothesis p minus 1 is 0 and our goal is p equals 1, and that should just require adding 1 to both sides. So linearist can do that. So we're not kind of obscuring our code, and that is actually the example in the example code that we kind of provide and have a look at. There it is. So you can look at the blog or the slides if you want to read in more slower kind of pace what's going on there. So if you wanted to read a little bit about that, you can. Interesting to see the definition of that lemma that we've been applying. So we did do that, and we saw that it says a times b is 0 if and only if a is 0, b is 0. So it's a good habit to get into. When you apply a lemma, look at its definition, look at what it says, to be sure that it's relevant for us, it's the right lemma for us. You can read this in your own time on the slides. That was the modus ponens we talked about. A bit of Latin, a bit of Harry Potter. Sounds like a spell, doesn't it? Cool. So we also talked a little bit about replacing the hypothesis rather than having an intermediate result, and we said it's fine because it's equivalent. So you'll find that in writing pen and paper proofs, we often have intermediate results because we don't go back and replace what we've written. We don't rub it out or draw an ink line through it. Whereas in Lean, you'll see it more often that the proof code actually manipulates hypotheses, so it replaces them with something that's equivalent. So that's just something we get used to. And we saw in the Infoview the action of applying that lemma. Let's do that again just to be sure. So before we apply the lemma, our hypothesis is a product, something times something is 0, and by the end of it, it's a disjunction. Something is 0 or something is 0. So that's the magic, that's the key. So nothing overly new today. The idea was to start using bidirectional lemmas, which are of the form if and only if they work in two directions. And the idea is to pick which direction that's relevant for us. So this easy exercise, and I say easy, again in the sense that the mathematics is not going to be hard, and the idea is to take what we've learned and modify it a bit, just to build confidence that we can do it. That's the idea. So we want to prove this thing doesn't equal 0, given this is not 0 and this is not 0. So let's draw a picture and write that down, because that looks a bit complicated. So we are given p does not equal, well, was it p? P minus 1, okay, so it's following the other pattern. So p minus 1 does not equal 0, and q minus 2 does not equal 0. And is it an and or an or? It's an and, that's important. It's an and. So both of these things are true. Tick, tick. So both of these things are true, and we want to prove somehow that p minus 1 times q minus 2 does not equal 0. You can see it's very similar to the task we've been looking at. And the key to it again will be to find a lemma that's relevant and use that. So you can see how these will be the hypotheses that we write in Lean. I won't do it for you, but you can see you can either write it in two ways. You can write this as one conjunction, or you can just write it as two hypotheses. So H1, p minus 1 does not equal 0, and then H2, q minus 2 does not equal 0. So that will be part of the proof header, and then the goal will be this thing here. What do we think the lemma might look like? Oh, actually, I've actually given you the lemma, so you don't have to search for it. It's mul ne 0if. Let's do a search on that official website. So if I type the name mul not equals 0 if, and it's that one there. So it's saying, yep, it's saying the product doesn't equal 0 if and only if one of the quantities is not 0, and that's an and, not an or. The other one is not 0. Does that match what we're trying to do? So how does this thing, the lemma that we've just looked at, how does that, this is the lemma, the mathlib lemma. How does this help us? Well, we have to start here and end up here. We start with a conjunction and end up with a product. This starts with a product and ends with a conjunction in that direction. So we want this direction, don't we? So you can see we'll have to apply it with a dot mpr to pick this direction, so that this matches our hypotheses and this matches our proof objective. That should be enough of a clue to get you going. I think I've given enough there. So I hope you have fun doing that. Any challenges, any problems, do comment, and we'll have a discussion in the comments to the video. Great. I hope that was fun. See you next time. Bye.